Okay, hello to CARTRE's webinar series, and this is the webinar number 8. The topic of today is key performance indicators and assessment of impacts of automated driving. First, a few words about CARTRE and this CAD initiative webinar series. So this is part of this joint initiative by 2 European coordination and support actions. One is called CARTRE and the other one is called SCOUT. It's a partnership of 30 partners and around 40 associated partners representing research, industry and different authorities in this field. And the goal of these projects is to bundle European and national actions to accelerate the deployment of automated driving. We have a webinar series which is aiming to present existing projects in this field and explore global issues in automated driving research. In Europe, we have different types of activities related to connected and automated driving. We have the annual conference, digital knowledge base, strategic guidance, position papers, data sharing and evaluation activities, and stakeholder network. There are several these thematic interest groups, and I will list them here shortly. So they are related to connectivity, socioeconomic sustainability, industrial production, human factors, big data and artificial intelligence, and infrastructure. In-vehicle enablers, safety validation, policy and regulation, new business models, and users and society. And then going to the agenda of today. So I will now I'm introducing you to the agenda of this webinar. Then I will shortly tell you about this trilateral impact assessment framework, which we have developed for assessing the automated driving. Then show you some results related to this key performance indicator survey that we just made. Then I will hand over to my colleague Adrian Slocki from IKA, and he will talk about safety impact assessment in adaptive project, and then give an outlook to safety impact assessment methodology for the ongoing L3 pilot project. And then in the end, for the last 15 minutes, we have a questions and answers session, so you can put your questions to the webinar tool, and then we will take a look at those in the end. But now I will go to this trilateral impact assessment framework and give you a short introduction on that. So what does it mean, trilateral? It means a cooperation between Europe, US and Japan. And 3 years ago, they performed or made a decision to make this kind of subgroup special for impact assessment activities in these 3 regions. We have now more than 40 members from all of them, covering research and authorities and decision or policymakers. And the objective of this group was the harmonization of high-level evaluation framework for assessing the impacts of automation in road transportation. So that was the high-level aim or the mission to do. And with this high-level framework, we were targeting both the designers of field operational tests and those who are making the impact assessment for automation, but also policymakers. And the motivation why they wanted us to do this is that the potential impacts of automation, they are very far-reaching and complex, and it's not so straightforward to assess them. There are also very high expectations on what the connected and automated vehicles can contribute to the societal goals. One reason, of course, is that field tests are expensive, and therefore it's important that they are designed so that we can maximize the insight obtained. And of course, internationally, it's always helps if we can make meta-analysis And if the evaluations across the world are complementary, and we can make better use of each other's findings. And of course, it's always good to exchange best practices. That's always beneficial for everybody. This is what the framework document looks like. This is the version number 1, which was published in January 2017, so a little bit more than a year ago. We will publish a new version in next month. The content of the framework includes introduction, system and impact classification, impact mechanisms, recommendations for experimental procedure, and some recommendations for data sharing, as well as conclusions. And as you can see, this is a book or framework that does not really go to the level of the single evaluation methods, as it depends so much on what you are evaluating, what are your research questions, etc., what is the best method. So we want to keep this on high level, as was our aim. So what does it mean, system and impact classification? Sorry. So we define several impact areas, and we divide them into direct impacts, those meaning that something that you can measure in a field test. Then there are those direct impacts. They will have indirect consequences or implications on other areas. So we have definitions for also those. And in addition to definitions, we provide recommendations for key performance indicators with which those impacts could be measured. And this is one of the key areas, or most important areas, where we will do changes for this version number 2 based on this survey that I will present shortly soon. So of course it also gives you instructions how to classify the system and design domain, so that the others who are utilizing your results, they would understand what is it that you have evaluated and under which conditions. Then impact mechanisms. The potential impact mechanisms are, well, we have tried to identify them, so that, and the motivation why to do so is to ensure that the assessment covers systematically both the intended and unintended impacts, the direct and indirect one, but also the short-term and long-term ones. And you look at the users of the automated vehicles, but also those who are the other traffic participants, the non-users. And even though you would not be able to assess all of these indirect, long-term, unintended impacts, it's good to acknowledge that they still may exist. The report gives some examples on how to describe them, and then, of course, depending on what you are assessing, you can create such graphs for your own study. Here is an example. The automated vehicle that can deliver itself, of course, it increases the convenience of car sharing, which increases the households replacing owned with shared vehicles, and then it decreases the demand for parking, which has implications for land use. So this kind of graphs can be then made. Then the framework provides some recommendations for experimental procedures. It gives basics for setting the study design. These are in line with the famous VIII methodology. There are other webinars to explain that. But then it goes also to the cases which are special for automation studies. So the topics like when it's not possible to test all those first automated vehicles in naturalistic environment, you may have control tests, you may have simulation instead of field tests, etc. So it's good to acknowledge what kind of, how does it affect then the evaluation. And also that these first field tests are performed with these prototype vehicles, and their performance is not the same as for the planned production vehicles, and that's also has some implications for scaling up the results, etc. And then we discussed there the data sharing. It gives reference to existing data sharing frameworks. It describes some obstacles for data sharing, and also gives some solutions to them. So these are, for example, related to competitive information, privacy sensitivity, sensitive data, different legal and ethical conditions in different countries or regions where you make the assessment, and to the fact that not always data can be easily accessible. Then relate some obstacles related to storing, maintaining, and opening data after the project. From cost-wise, that how to handle that after the eligibility period of project has ended. And of course, in the future versions of framework, it would be nice to provide a recommendation on what data could be shared, but this is not given in this version number 1. As I said, the framework document is available. You can access it from connected and automated driving.eu website. It can be found from the library. Here is the link. You can find this slide set from the website after this this webinar, and you can click the link. But you can also find the version number 2 in April from the same library location. I cannot make the link here yet as the report is not there yet, but it can be found anyhow. Then I will go to this trilateral key performance indicator survey. This is very recent report published in February this year. So when we made the first draft of this trilateral impact assessment framework, we noticed that it's very difficult to provide recommendations on those key performance indicators that should be utilized by all the impact assessment studies in this field for all those impact areas. So we decided to make a survey and collect feedback and views on which are the most important ones for different areas. And last year in springtime, we designed this survey, and then it was open from June to November. And in total, we got 77 answers from covering EU, US, and Japan. We had approximately half of the respondents were representing different research organizations, but we got also policymakers and authorities and industry members providing their views. And now the results that we have obtained, those will be utilized in the update of this framework document, so that the recommendations that we will now make there are in line with the common view on what is which are the most important impact KPIs in this field, or for every single impact area. So the survey was structured such that first the respondent tells from which region he or she comes from and what sector does he or she represent, meaning these research, industry, policymakers, etc. Then they identified the impact areas of interest, or where they have expertise. So these lists has a long list, you can see from the slide, going from vehicle operations to economic impacts, and it covers the same areas as the trilateral framework. We had there always a short explanation what is meant by each area. Then what is important or more important or less important key performance indicator? Of course, it depends partly on what kind of transport system you are assessing. Are you looking at automated passenger car, shuttle bus, or truck, or are you looking at mixed traffic? And therefore, we decided to let the respondent to choose what kind of vehicle type they would have in mind once they are answering or rating their KPIs. And also they could choose which kind of automation level they are looking at. Are they looking levels 1 or 2? Is it 3, or is it 4 to 5? So those they chose in the beginning, and then they gave ratings to those areas that they had ticked that they have expertise in or interest in. Scale was from 0, not at all important, to 6, extremely important, and then we had in addition this not applicable, if we suggested something that they didn't see that made sense for that particular system. In addition, they had possibility to propose additional key performance indicators, and those are also all listed in the report. And all those will be also listed in the updated framework document. I will now give you just I'm not going to read all those key performance indicators and the ratings that they got, but I will just show you examples of the tables that you can find from the report. So first we have these overall average ratings where not applicables have been taken out. And then we have calculated the averages, so you can see always the KPI and then the average, and you can see also the number of answers giving to that particular KPI. So that was average over all the data, and then we have the same tables, but now they are the answers, or the ratings are divided based on the SAE level that they had chose. So different or certain KPI might be different for low level automation or higher level, but not the other way around. So you can see the differences here. In addition to that, also we had a lot of respondents had chosen the automated passenger car or the mixed traffic. There were very few answers for the trucks and shuttle buses, so those are not reported here. But these two different views you can also see separately. And then we have those individual distributions of answers. They can be found from the annex. So if you want to take a more close look how did the answers spread, or what was the distribution, you can also do that based on the annex. Some overall observations about the results. Well, none of these KPIs received very low ratings. This is partly due to the fact that we had a rather large group of experts selecting these KPIs that we would propose in the survey. So we were like 20 persons designing it over the last springtime. And of course, those that we saw already irrelevant were dropped out. And but also it can be partly because the impacts of automation, they are still partly unknown, or even mostly unknown. So the experts are interested in many potential impacts, and it's not so focused only on one or two areas. So that's also gives that they had rated several KPIs rather high. You can also note when you take a look at the KPI definitions that they are not extremely precise. So it, of course, if you want to then calculate certain KPI, you need to make more precise definition of what is meant by each and every one of them. So harmonization will be needed even after this, but this gives more indication on those KPIs that could be utilized and which should be then worked further. And as already has been mentioned, that will be in the version number 2 of this trilateral impact assessment framework that will be published in April, now in a few weeks' time. So this is what I had in mind about these trilateral activities, the framework and the key performance indicator results. And now I will hand over to okay, sorry, one more slide on this. So you can also find this key performance indicator report from the CARTRE website. By clicking this link, you can find it from the library section there. And then I will hand over the presentation to Adrian. So he will now tell you about safety impact assessments.
Okay, hello everybody. My name is Adrian Slocky. As you can see, I'm from IKA, which is an Institute for Automotive Engineering at the Aachen University from Germany. I'm going to talk today about safety impact assessment, how safety impact assessment is performed, especially on focus for automated driving. And I'm going to utilize at the beginning the example of Adaptive, which is a research project of the European Commission, which ended in summer last year, where we performed an impact assessment. for automated vehicles. And in the end, I'm going to talk about the L3 pilot project, which is an ongoing research project where we try to collect some data, utilizing this data to perform an impact assessment based on real data coming from vehicles on the road. Let me start with the next slide, where I just give a short introduction on evaluation methodologies on different test levels. You can see if you have an automated driving functions, which usually has a sensor, an algorithm, an HMI, and some interaction with the vehicle. You can test such function on different levels. You can start with the sensor itself, with the perception, with the sensor fusion, with the function, with the interaction with the human driver, if he needs to interact, if he needs to come back in a level 3 system. You can test, of course, the actuators and so on. And if you operate such a vehicle in a real environment with surrounding traffic, other traffic participants, then we talk about an impact level where we can perform the impact assessment. So our goal is to predict how changes will occur due to vehicle automation. In our case here in the webinar, I will focus on safety. Of course, you can also perform impact assessment based on environment, on how much emissions, for example, your vehicle provides, or on socioeconomic impact, so cost acceptance, cost benefit analysis, and so on. But as I said, I'm going to focus on safety. In the next slide, you see different methods where you can collect data for your impact assessment, for your safety impact assessment. First of all, you can start in simulation, where you have the driver, the vehicle, and the environment in a virtual environment where you have a very high reproducibility, you have very low simulation costs. But of course, you need to simulate very well, or as well as you need to do that, and you have other constraints. The next level would be a driving simulator, where you can test a real human, the interaction especially, with a mock-up vehicle, so a kind of virtual or artificial vehicle in an artificial environment. On the test track, the control field, you have a real vehicle with a real driver, but the situations which you are testing, they are artificial because they are somehow staged with balloon cars or other tools. And finally, you have the field operational test or a naturalistic driving study, where you have the real vehicle in the real environment with a real driver. You can imagine this is, of course, the most expensive form of collecting data, since you need to have the function completely available, completely safe, so that you can actually operate it in a real environment. And that is not always the case, especially not in the development stage. But naturally, you get the most interesting data from this field operational test. And when you have a function which is not yet on the market, we call it a pilot. And that's all what the L3 pilot is about, which I will talk about a little bit later. In the adaptive project, we focused a little bit more on simulation and in the control field, which you can see on the next slide. As I mentioned, adaptive. Sato, can you please build up the whole slide? I think animations doesn't make so much sense. In the adaptive project, we had different prototype vehicles which were available with very different functions. We had, as you can see here in this picture, for example, a highway chauffeur, so a level 3 highway automation function, or we had a valet parking function, which you can see. And we tested within adaptive in simulation on special test tracks, but also in reality. And we tested different methods, and we collected different data. There was, of course, the technical assessment, where we focused very much on the behavior of the function. We also did a user-related assessment, so testing the interaction of the user, how many times the user had to take over, how the takeover was designed. And also we tested the in-traffic behavior, how other traffic participants, so other vehicles, which you can see here in this picture, reacted on the automated function. And we used all these data sources to perform the impact assessment, which I'm going to talk about in more detail in the next few slides. In order to perform an impact assessment, which you can see on the next slide, you need to have, of course, a baseline. So you want to test an automated driving function, and when you want to calculate the impact of this function, you need to understand what are you calculating against. So what is the state of the art today where we have no such automation function on the road? Therefore, we were asking ourselves, what is normal driving behavior? Satu, can you please also build up this slide? There are some more. Yeah, thank you. So basically what we can do is we can measure one person driving around in real traffic, but that is not enough. So what you can see here, we need a number, a high number of persons, so that we actually can understand how the traffic works today, how drivers are working today, and then see what the automation function is doing and calculating the differences and therefore the impact. In our case, we were quite lucky because we could use data, field data, which we collected in the past. There was a former research activity which is called EuroFOT. So it was a field operational test in Europe where we already collected a lot of baseline data which we had available. So the baseline was available. On the next slide, you can see once you have the baseline, you need to understand in which scenarios an automated function works. And in order to understand the scenarios, you need to classify the scenario. So you collect a lot of data, and then you need to process the data and find scenarios in the data. So just a simple example, you are driving on the motorway and there are different scenarios like overtaking, like lane changes, or a very simple scenario is just simple following. So you follow a car in front of you. And in order to analyze the data, you need to understand in which scenario you are in. So you are trying to cut the data, cut a complete drive into single scenarios, and you can do that in different methods. One very simple method is just you set up some rules. So this is work which my colleague Mohamed Ben-Mimoun has done in his PhD thesis, where you just find some rules for situation classification. You apply those rules by hand, and then you have all the situations which you need. That is, of course, only possible if you know all the situations which you occur. So it's quite limited. Once you don't have a rule for a certain situation, this situation is maybe not classified or falsely classified. What we did in Adaptive is we developed a machine learning-based classification algorithm. This was done by my colleague Christian Rösner, 2016, which you can see here on the right side. And if you click a couple of times, you see the differences between the rule-based and now the machine learning-based, where you of course need a training set of data in order to train the machine learning classifier. But we had this data available from EuroFOT, where we had a lot of rule-based annotation of scenarios, and all the classification was available. So this is something which we needed in order to perform our assessment. And on the next slide, you can see the overall assessment which we performed in Adaptive. So on the left side, you see the different data sources. So from EuroFOT, the reference data, and from the demonstrator vehicles, actual data of the function behavior. So that is the automated driving function, which you see here under demonstrator function. Then we had the classification of the scenarios, which we solved by machine learning algorithms. And then we have the scenario-based assessment on the right side, where you see a change of frequency of the scenarios, and of course a change of effect within the scenarios. And if you bring that together, you can calculate the impact assessment. There are some results, of course, available. I can only show you some examples here. The adaptive website is still ongoing. If you are looking for detailed results, you can see or you can find the deliverables on the adaptive website. If you just type adaptive project into your browser, then you will find the adaptive website. And when you look for deliverables, you can see the results there. On the next slide, I show you some first results. Or here, yeah. So here you see some first results from the technical assessment. So here you can see a comparison between Euro FOT and the adaptive function. The Euro FOT was the baseline, so the human driving is the best baseline. And you can see here an example of the adaptive highway chauffeur, and this is what shows here is the change of frequency in maneuvers over time. You can see there's an overlap, and in the top figure you see the duration of a lane change as one example scenario. And you can see it's much more uniform with automation than by manual driving, which is kind of it was expected since the automation function is following a certain algorithm and the human driver is driving as he likes. And in the bottom figures, you see here the change of time headway in vehicle following, and here the frequency. You can see it's lower, so there's much less variability with automation, and of course this can be quite easily explained again since there's a function available and the driver is not really driving itself. So that is basically some first results for the technical evaluation, and we use this result then to actually calculate based on such a data. This is, again, just an example, but this is the input data which we need to calculate the impact. And if we go to the next slide, this is just one more example. Satu, if you click once again, thank you. This is the change of frequencies. I mentioned before that you have two changes, the change of effect and the change of frequencies of the situation. And here again, you see the comparison between the reference data from the human driver from Euro FOT in blue and the adaptive highway automation. And you can see small increase of lane change scenarios and a little bit higher increase of cut-in scenarios. So basically, in this results, you see that the behavior of the scenario, the effectiveness scenario is different, and the number of occurrence or frequency of the scenario changes when you have an automation function compared to the human driver. And on the next slide, you see on the next slide, you see the methodology for the calculation of the actual impact assessment. So we have our function, which you can see here in the middle. There's a very much detailed description of the function. We have our accident data, which we can take, for example, from in-depth databases. Here's the example of the German in-depth accident database. And we take our situations. Of course, the most important ones are the critical and relevant situation, where we have, for example, strong braking or short distances. And then we use this, and we need, of course, simulation. Because in adaptive, we could test our function only for short times. So basically, we had one vehicle only, which was driving around on the public motorway, on the public Autobahn here in Germany. But you can imagine the data that we can collect in such a project is quite limited. So adaptive was not really a field operational test where we had a high number of vehicles driving around in all Europe, but we only had this one vehicle where we are able to collect the data. And since this data is quite limited, we needed to simulate the traffic scenario based on the function description and based on the data. And once we did that, we then have top scenarios. These result from simulation, from the description of the function, where this function can actually support, and of course from the data coming from the accident database. And in the next slide, I have some one simple example for such an top scenario. You can see it here on the right side. This is called obstacle in lane. So we have a scenario of a 3-lane motorway. Here in the example, it's 4 kilometers long. And there's an obstacle placed in the central driving lane in a position in front of us. So somewhere outside the viewing range of the sensors. And then there's surrounding traffic, which we actually have, which we simulate according to stochastic variations. And then we have some vehicles, which you can see here in this picture, in this lighter blue color. These are the vehicles which are equipped with the functions. These are the relevant vehicles. And then we have in these vehicles the automation function, or we have the baseline, so meaning the human driver, where we have a driver model based on the data from the baseline. And then we can, in simulation, change the parameters any way we like. We can test much more than the real data, since we don't have so much real data available, and then calculate the impact. On the next slide, of course, we also have to talk about some limitations of this study. There's, especially for level 3 systems, transition of control, which might cause negative effects. So we didn't study these in much detail. Then we have effects along with the penetration rate. So meaning if we have a very high penetration rate, maybe most of the vehicles are automated, these can cause different effects. Since today, you might know, many of the drivers out there are not really driving according to the traffic rules, especially in traffic jam situations. The distances are much shorter. This allows us today to have some traffic flow, which is still manageable. If all the drivers would really drive according to the driving laws which we have, then many more traffic jams would occur and the traffic flow would be impacted quite negatively. So we didn't really consider these effects in our study. The usage was not considered. We did not consider that drivers might turn on this function, but maybe also might not use the function, although they have it available. And of course, the available data was quite limited, as I mentioned before. So these are some boundary conditions. And due to these boundary conditions, Satu, if you click further, we started a new project, which is L3 Pilot. As mentioned before, level 3 pilot. So we're going to collect data, hopefully from over 100 vehicles and over 1,000 drivers from all over Europe. So it's a large scale level 3 piloting. It's funded in the Horizon 2020 program. We have a total of 34 partners within the project, all the European OEM, who almost all provide vehicle. We have a very nice budget of 68 million. And if you want to have more information, there's the website l3pilot.eu. And the website is already up and running. We just started this project in September, so it's still quite fresh. And basically what you see here on this slide is the Festa V. We have 3 phases where we're going to prepare the driving. We're going to collect at the moment, especially research questions and work on the methodology, which my colleague Satu is responsible for and doing a lot of great work on that. Then we're going to prepare the data collection tools, data logging. What kind of data do we need? What kind of data can we log? We're going to prepare the study design. Where are the vehicles able to drive? Which kind of drivers are able to drive the vehicle? How often? How much? And so on. And then we're going to have a second phase where we actually have vehicle on the road driving in level 3. This is the actual piloting phase. And in the end, we're going to collect all this data and evaluate the data. So here we at IKA are responsible for the evaluation. So different than in adaptive, we want to do less simulation and work more with real world data, which we collected out of the vehicles. There's going to be technical data on the one side, and of course user-related subjective data, where we want to also take into account all the limits that I mentioned before on the usage of the function, of the acceptance of the function, and so on. And in L3 Pilot, we also want to perform a socio-economic impact assessment. And on the last slide, you see some more details on the impact assessment, which is really a scope of L3 Pilot. So you see here in this nice little picture that we have different levels. We have, first of all, the single vehicle level where we collect data from a single vehicle, but then we want to scale it up on a fleet. So more than one vehicle with a similar or ideally with the same function driving around all over Europe. And in the end, we're going to scale it up on European level. And we're going to do some technical and traffic evaluation, some user evaluation, then especially the impact evaluation. Again, we're going to focus on the change of frequency of relevant situations and, of course, on the change of effects in these situations. And here we're going to focus on safety and on environmental impact as the main two focus. We have some more impact areas, but really safety is the most important. And I think due to the current discussions, especially in Germany, also environmental impact is quite interesting. In the end, we're going to go one step further and perform a cost-benefit analysis on socioeconomic impact level. And I think it's going to be quite interesting. The project, as I mentioned, just started in September, so we are in phase 1 at the moment, preparing everything. So it will take some more months and maybe a few years until we have all the results, but I think the research question is going to be quite interesting. And that is the end of my slides. With that, I would now try to start a question and answer session. I think we have 10-15 minutes for that. So if you have any questions, please type them in, and I hope it will reach us so that we can answer them now.
While we are waiting for the potential questions to come, well, maybe we can also go through this how to stay with us and the results of the support actions. So you can visit the connected automated driving.eu website, and there is a section for webinars, so you can always go back to those. You can find us on Twitter. We have a newsletter that you can subscribe to. And if you are interested, you can also become an associated partner to this project. And you can send email to this partnership at connectedautomateddriving.eu address for that. But do we have any questions? I do not see any questions. So if everything is clear, I guess we can end the webinar, and we want to thank you all for participating us today.